should do. You should bang your head against the wall with that problem before you jump to my solutions. That's how you're going to make that progress.
I was hitting your head against the pillow after I went to sleep.
No, it's got to hurt. It's got to hurt.
Yeah, feel it.
All right. Today we'll just be doing a really quick short lecture with something that's fairly intuitive. And then we'll spend the rest of the class going over homework problems and then the test. Make sense?
Yeah.
Yes.
All right. So today we're introducing one of the most ubiquitous objects in mathematics, a relation. Relations show up everywhere. You need to understand a relation. If any of the things that we say today you don't perfectly understand, we need to go over it again. It's very simple, but they show up a lot. You need to understand them. This is one of the things that is going to repeatedly show up throughout the rest of the class. Boolean algebra, you're not going to have to do a lot of Boolean algebra from here on out. Relations, you'll be using this from here on out, and you'll be using it the last week of class. We'll still be using relations. Never go away. All right. So what is a relation? Real simple definition. A relation is a set of ordered pairs. You remember what an ordered pair is?
Mm-hmm.
It's a list with two elements. So a relation is a set where everything in the set is an ordered pair. That's it. That's simple. Right? Okay. Example. Is this a relation or not?
Yes.
Yes?
Yes.
What? That is not an ordered pair. That's a set with three elements.
That's not.
So is this set right here a relation?
That is a relation. It's all in an ordered pair.
Yes, this set right here is a relation. Let's look at what's in this set. The first thing in this set is the ordered pair containing 1, 2. Next, what else is in the set? The ordered pair containing the set 1, 2, 3 and SpongeBob. Everything in this set is an ordered pair.
I didn't see that as a parenthesis.
And so it's a relation. Sorry, that's a parenthesis. Okay. Next. Is this a relation?
Yes. Everything in it is a set.
It's not.
Or
Not in order.
it has everything in it.
If everything in it is a set, can everything in it be an ordered pair?
Everything in it is an ordered pair.
That right there. Is that a relation?
No.
No. There's no ordered pairs in there. Wait, that's not what we said. What was our
Yeah,
definition?
everything is-
A relation is a set of ordered pairs. Is everything in here an ordered pair?
Yeah.
Yeah, everything in there is an ordered pair. So it is a relation.
Okay.
Everything in it is an ordered pair.
Okay.
So it's the empty relation. Make sense? Wonderful. All right, one more. Here's how you'll mostly see them throughout this chapter. R is equal to the relation 1, 2, 3, 4, 5, 6. And here's often how you'll mark it. R, some variable name, equals, and then some relation. Make sense? Pretty straightforward?
I thought a relation had to have only two in it. Only two. ordered
A
pairs.
relation is a set of ordered pairs.
Oh.
Look at R. That's an ordered pair, that's an ordered pair, that's an ordered pair.
Oh, okay, that just clicked. Okay.
Wonderful.
That makes sense.
Okay, relation. A set of ordered pair. A set where everything in there is an ordered pair. It can have infinite elements in there. It can have no elements in there. Good?
Yeah.
Okay. Notation that we often use with relations. So if the ordered pair xy is in our relation R, rather than writing it this way, we often use this type of notation when it's a relation. We say x, r, y. X is related to y. So looking up at this relation R, true or false? 1 is related to 2.
Yes.
True, because 1, 2 is in the relation right there. What about 3 is related to 4?
True.
What about 5 is related to 6?
True.
What about 1 is related to 3?
Not true.
Not true. So here's how we say they're not related. We put a line through it. Let's try one more here. 2 is related to 1. True or false?
Not true. True. False.
2 is related to 1. True or false?
False.
False. It's a list.
False. 2 is related to 1. What does that mean? If 2 is related to 1, that means the order pair 2, 1 is in R. Is the order pair 2, 1 in R? No, 1, 2 is in R. That's something completely different. So that's false. 1 is related to 2, true. 2 is related to 1, false. Make sense?
Yeah.
Okay. Let's do another example. We're going to look at the set of all ordered pairs xy, where x and y are integers, and y minus x is a natural number. With me? And I'm going to name this relation some weird symbol. I'm going to do like a piece of a triangle, and instead of putting the line there, I'm going to put it there. Right? Just some weird made-up symbol. You with me? Question. Is 3, 7 in this relation?
No. No. Yes. Yes, it is.
What does it mean for
Oh,
3,
yes.
7 to be in the relation? Is the right-hand element minus the left-hand element a natural number?
Yes.
What's 7 minus 3?
4.
Is that a natural number?
Yes.
Okay, so yes, it's in the relation. Let's try this again. Is negative 9 and negative 2 in the relation?
No.
Yes. Yes.
No.
What's negative 2 minus negative 9?
7.
7. Is 7 a natural number?
Yes.
Okay, so it isn't. Is 2, 5 in the relation?
Yes.
Yeah.
What's 5 minus 2?
3.
3. Is 3 a natural number? Wonderful. What if instead I had this written 2, 5? Would that be in the relation?
That's the same thing.
So you wrote
Oops,
it.
5, 2. 5, 2. Is that in the relation?
No,
No.
because it's negative 3.
What's 2 minus 5?
Negative 3.
Is negative 3 a natural number?
No.
No. So that is not in the relation. Now, here's one way that we could write it, but using our new notation that we have up there, let me rewrite these things. 3, our relation name, 7. Negative 9, our relation name, negative 2. 5, our relation name with a line through it, 2. And you're very familiar with this relation. We say 3 is less than or equal to 7. Negative 9 is less than or equal to negative 2. 5 is not less than or equal to 2. So, less than or equal to, it's a relation. Here's its relation for the...
Oh, well. That's cool.
Yeah, so there's an actual definition for less than or equal to on the integers. Now you know what that symbol means.
Cool.
Learning your inequalities. Crazy, huh?
Yeah.
Is 0 a natural number?
0 is a natural number. So 5 would be less than or equal to 5. How do I know that 5 is less than or equal to 5? Because 5 minus 5 is 0. 0 is a natural number. If we call this relation the less than or equal to relation. Just a name.
Okay.
Good?
Yeah.
And obviously we could come up with the relation for the other relations that you're used to in mathematics. You're used to the less than relation. You're used to the congruence relation. A lot of relations that you come across. Okay. So now let's define what it means for R to be a relation on a set. Before we do that, let's remind ourselves of cross product. Make sure we remember cross product. Look at A here as a set. Actually, let's make our own slightly smaller. Let's say A is equal to the set A, B, C. Do we remember what A cross A is?
Yeah.
What is it?
Wait.
A, A, B, B, C.
AA, comma, AB, comma, AC, comma, BA, comma, dot, 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 all the way to CC. Right?
Yeah.
So we're clear on the cross product?
Yeah.
Mm-hmm.
Alright, so hopefully this definition makes sense. Let R be a relation. So R is a set of ordered pairs. And let A and B be sets. We say that R is a relation on A, provided that R is a subset of A cross A. So what's A cross A going to be? It's going to be all the possible ordered pairs you can make, where your first element comes from A and your second element also comes from A. R is a relation on A if R is a subset of A. In other words, if all the ordered pairs that R uses are elements of A.
Okay.
We'll see some examples of this in case it's not clicking, but so if R is a subset of A cross A, R is a relation on A, where it only uses the elements in A. And we say that R is a relation from A to B, provided that R, wrote that backwards, provided that R R is a subset of A cross B. R is a relation from A to B if it's a subset of A cross B. All its first elements, all its left-hand elements come from A, and all its right-hand elements come from B. Then it's a relation from A to B. And we think about it as mapping 1 to 2, 3 to 4, 5 to 6. Okay, let's do some concrete examples to make sure that we're getting this. Here's our set A, here's our set B. 1, 2, 3, 4, 4, 5, 6, 7. Question, is R a relation on A? Yes or no?
Yes.
Yeah.
You sure?
Yes,
Oh.
again.
Yes.
Is R a relation on A?
Yes.
How do we know if R is a relation on A?
Every
If it's a subset of A cross A.
Right, is R a subset of A cross A? That's one way you can think about it. Here's another way you can think about it. Are all of R's left-hand elements in A?
Yes.
Are all of R's right-hand elements in A?
Yes.
Then R is a relation on A. And if in this case we were to write out A cross A, then that would have been 1, 1, 1, 2, dot, 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 all the way to 4, 4. And we definitely would have written out these 4 elements. So R is definitely a subset of this A cross A.
Yes.
Okay, so this is a relation on A. Is that a relation on B?
No.
No.
No. Is it a relation from A to B?
No.
No. Cool. Let's go to the next relation. S. Is S a relation on A?
Yes. Yeah.
Yes, so this is on A. Is it a relation on B?
No.
Is it a relation from A to B?
No.
Is it a relation from B to A?
No.
Cool. So look at this one. Is this a relation on A?
No.
No.
Yes.
No, it's not.
No.
Yes, it is.
No, it's not.
Yeah, it is.
7,
Seven's not in
4,
A.
5.
The element 4, 7 will not show up in A cross A.
Yeah.
Oh, I'm thinking A to B.
Yeah.
Okay, so it's not on A. Is it a relation from A to B?
Yes.
Yes.
Yes. So this is a relation from A to B. We often signify that with an arrow. A to B. Is there a relation on B?
No.
No. Is there a relation from B to A?
No.
No.
Okay, next. Is this a relation on A?
No.
No.
Is there a relation on B?
Yeah. No.
No.
No. Is there a relation from A to B?
No.
No. No.
5
Is there a relation from B to A?
Yes.
Yes. So this is a relation from B to A. All the left-hand elements are in B. All the right-hand elements are in A. Everyone following this?
Yes.
All right. What about V? Is that a relation on A?
No.
No.
Yeah.
Is there a relate?
No.
Is there a relation on B?
No.
Is there a relation from A to B?
No.
Is there a relation from B to A?
No.
No. So it doesn't have to be one of them. These all happen to just be one of them. Doesn't have to be.
Wait, I have a question.
Go ahead.
Can it just be from A to B and B to A? For example, 1, 7 will show up if you do
A to B.
A cross A, or A cross B, and 7, 1 will show up if you do B cross A. So if you do the both, then you could get 1,
No, because
1
it
7,
has a five
7
for both.
It's all in one set.
Yeah.
I think the answer is no to your question, but it sounds like they followed your question better than I did. All right. Last relation, W. It's a relation right here. Is this a relation on A?
Yeah.
Yes.
Yes. Is it a relation on B?
Yes.
Yes.
Yes. Is it a relation from A to B?
Yes.
Yes.
Yes. Is it a relation from B to A?
Yes.
Yes. So it can also be all 4,
Yes.
right?
Yeah.
Okay. So there's a bunch of examples of different relations on sets or from one set to another set. Pretty straightforward? Cool. All right, next. Let R be a relation. The inverse of R which is denoted with r to the minus 1 exponent. Now that is not an exponent. We're not saying it the same way that 2 to the minus 1 is equal to 1/2. We're not using it this way. Same notation, completely different meaning. How many of you have seen inverse functions?
Like trig?
In like trig or algebra? F to the minus 1, we mean it that way. If you've seen the notation that way before. If you haven't seen the notation before, fine. Here's what we mean by it. Just know that this has nothing to do with an algebra exponent.
Are you listening, Steve?
Nope, they're out here. Okay. So the inverse of r, which we denote with r to the minus 1, is a relation formed by reversing the order of all the order pairs in R. So take each order pair, flip it around, that gives you the inverse. That's all there is to it. And that's what you were doing when you talked about inverse functions, for those of you who had inverse functions before. Same thing. So let's look at an example. So if R is a set 1, 1, 2, 2, 3, 3, 4, 4, R inverse is going to be what you get when you flip all those around. So instead of 1, 1, we have 1, 1. Instead of 2, 2, we have 2, 2. Instead of 3, 3, we have 3, 3. Instead of 4, 4, we have 4, 4. So taking the inverse doesn't necessarily change the relation. Let's look at S inverse. S inverse at 1, 2. Instead of 1, 2, we have 2, 1. Instead of 3, 2, we have 2, 3. Just flip the order. If T is that relation, T inverse is, instead of 1, 4, 4, 1. Instead of 1, 5, 5, 1. Instead of 4, 7, 7, 4.
Good.
All right, finally, you tell me what to write.
4, 4,
4, 4,
2, 5,
2, 6.
2, 5,
2, 6,
2, 6, 3, 7.
2, 6, 3, 7. All right, let's look at R. Is R still a relation on A?
Yeah.
Yes. So if R was a relation on A, its inverse is still going to be a relation on A.
Okay.
If all the left-hand and right-hand elements of that were elements of A, then when you take its inverse, all the left-hand and right-hand elements are still elements of A. S inverse, that was a relation on A. Or S was a relation on A. When we take its inverse, it's still a relation on A. This is still on A. T, that was a relation from A to B. When we take its inverse, what type of relation do we have now? Instead, now it's from B to A. Because we flipped the order. Instead of mapping everything in A to, or instead of mapping elements of A to elements of B, now we're mapping elements of B to elements of A. Right? And finally, U inverse, what's it?
A to B.
This is now a relation from A to B. Good?
Yep.
Inverse relation. Pretty simple. All right, let's do a quick proof. Let's see, we're proving if R is a relation, then R is equal to the inverse of the inverse relation. In other words, if I take the inverse of a relation, I take its inverse again, I'm back to where I started.
Yeah.
Make sense?
Yep.
All right. 1. Let R be a relation. That was a terrible way. That wasn't much better. All right. How do I prove that two sets are equal? I need to show that everything in this set is in this set, and then everything that's in this set is in this set. Right? You've been doing a bunch of these? So, 2. So first, I'm going to show that everything in this set is in this set. So let xy be an element of R. Grab a random thing out of R. R is a set of ordered pairs. Right? Now if xy is in R, that implies that yx is in R inverse. By definition of an inverse. What's the definition of our inverse? If xy is in R, then, I don't think we went over this, sorry. R inverse. Here's a way that you could define the operation. The inverse of a relation is defined to be the set of all ordered pairs yx, where xy was in R. So if xy was in R, yx is in R inverse. Sorry, forgot to do that. So that gives you a concise definition that you can then use in proofs. So by definition, if xy is in R, then yx is in our inverse, using this definition.
Yep.
Similarly, if yx is in our inverse, then we know that implies that xy is in our inverse's inverse.
Square box.
No, all I did was show that everything in here is in here. Now I need to show that everything that's in here is in here.
Okay.
You gotta do it both ways.
Yeah.
Alright, so now 3. This time we're gonna say let xy in R inverse.
Oh, right.
Didn't give myself space right there. In R inverse inverse. Right? Now, if xy is in our inverse inverse, that implies that yx is in what?
Our inverse.
Our inverse. Which implies that xy is in what?
R.
R.
Okay.
4. Therefore,
Square box.
square box basically, but therefore R is equal to R inverse inverse. Nice and easy, right? Okay. Now, 5 properties a relation can have that we're interested in. 3 of these will show up over and over and over again, but let's get used to all 5. So, properties of relation. Let R be a relation on some set A. Then we call the relation reflexive, provided that for every x in A, x is related to itself.
Okay.
So here's a bunch of examples of relations. We're going to identify which of those relations are reflexive. So let's make sure that we understand each of these. Oh, I'm going to go off the screen. Good thing I caught that. Yeah, we're good. Okay. So let's start with R. Shoot, now you can't see the relation R. How far can we go? I made my screen too dark. Look on that phone and tell me when you can still see my chalk.
Yes. You can go a ways. Yes. Yes. Stop.
So somewhere like right there?
Yep.
Alright, let me just rewrite out R really quick right here. Someone just read R to me.
One set of one.
Oh yeah, this one was
Two,
awesome. 3, 3, 4, 4. Okay? S was,
1, 2. And 3, 4.
and what?
3, 2. T
W?
was 4, 4. We ordered pair 4, 4.
Alright, so those are the only ones that we have from there. With these 3, it was understood that the set A was 1, 2, 3, 4. So I just picked the relations that were relations on A. Because notice that reflexive property, let R be a relation on some set A. This only makes sense if we have relation on some set A. Alright, so when is it reflexive? A relation is reflexive if for all x in A, x is related to itself. Let's look at R. Is it true that for every element in A, that element is related to itself in R?
Yes.
What are all the elements of A? 1, 2, 3, 4. Do I have 1 related to 1, 2 related to 2, 3 related to 3, and 4 related to 4? Yes. So this relation right here is reflexive. Reflexive. What about S? Is S reflexive?
No.
No, we don't have 1 related to 1, we don't have 2 related to 2, we don't have 3 related to 3, we don't have 4 related to 4. So no, it's not reflexive.
So
What about W? Is W reflexive?
Yes.
Yes.
No. When is it reflexive? If for all x in A, x is related to x. Since A, in this context, was a set 1, 2, 3, 4, we have to have 1 related to 1, 2 related to 2, 3 related to 3, and 4 related to 4. We do not have that here. This is not reflexive.
Okay.
Make sense?
Yep.
Alright. Now for all these other ones, the set A is implied from context. If I'm talking about equals, the set A is all numbers. If I'm talking about loves, the set of A is all people, etc.
Okay.
Okay, so let's go over each of these. Is equal reflexive?
Yes.
Is it true that x is always equal to x, no matter what number it is?
Yes.
Yes, so that is reflexive. Congruent. Is every shape congruent to itself?
Yes. No? Same size, same.
Is every triangle congruent to itself?
Yeah.
Oh, to itself, yeah.
Yes. You guys did some basic geometry, right? If I draw some triangle, does that have all the same side lengths as that triangle?
Yep.
Does that have all the same angles as that triangle?
Yeah.
Yes, every triangle is congruent to itself. Every shape is congruent to itself. Yes, that is reflexive. All right, what about less than? Is every number less than itself?
No.
No. What about less than or equals? Is every number less than or equal to itself?
Yes.
Yes. Is 6 less than or equal to 6?
Yes.
Yes. Is pi less than or equal to pi?
Yes.
Yes. So this one is reflexive. Loves. Does every person love themselves?
No.
This is deep. Yes.
We'll assume yes. You could argue about it one way or another. We'll make a judgment call. Yeah, they do. Divides. Does every number divide itself?
Yes. Yes. Because you can
Yeah.
times it by
Does 5
one.
divide 5?
Yes.
7 divide 7? Negative 3 divide? Yes. Every number divides itself.
0 doesn't divide 0.
You can times 0 by anything. It divides itself one by the other number.
Can I find an integer such that 0 times that integer gives me 0?
Yeah.
Yeah, 27 trillion. 0 times 27 trillion is?
Or just 5.
Or just 5. Right. Okay, same last name. Does every person have the same last name as himself?
Yes.
Yes.
Yes. So that is reflexive.
Okay.
Ancestry. Is every person an ancestor of themselves?
No.
No. So it's not reflexive. Parent. Is every person a parent of themselves? No. Sibling. Is every person a sibling of himself? No.
Kind of.
Kind of. We'll make, these things aren't always well defined, like we have even is well defined, right?
Yeah.
We'll pretend that we have some well defined notion of sibling where that one comes out false.
Okay.
We'll say you can't be a sibling of yourself.
That's part of the definition.
Dang it.
Okay, so that was reflexive. Hopefully you got good intuition for reflexive.
Okay.
Let's move to the next one. Irreflexive. What does irreflexive mean? This is not the same thing as not reflexive. This is not the opposite of that. Students often get confused by that. Similar names, don't get confused by it. This is not the opposite of this. So what is irreflexive? A relation is irreflexive provided that for every element in A, it is not the case that that element is related to itself. In other words, no elements are ever related to themselves. Example, is R irreflexive?
No.
Is it true that no element is ever related to itself? No. Is S irreflexive?
Yes.
Yes, so this one is irreflexive. Is W irreflexive?
No.
No. Notice that W is not reflexive and it's not irreflexive. It's neither. So it doesn't have to be one or the other. Okay. Equals. Is equals irreflexive?
Yes.
No, it's not.
We just said it's reflexive.
Yeah, it's not. It's not opposite, it's that.
Right. What does it mean to be irreflexive? It means no element is ever related to itself. Is it true that a number is never equal to itself? No. Is it true that a shape is never congruent to itself?
No.
No. Is it true that a number is never less than itself?
Yes.
Yes. So this one is irreflexive. You can never have 2 less than 2. You can never have 5 less than 5. You can never have x less than x. Loves.
You missed one.
No.
Oh, less than or equal. Is it true that a number is never less than or equal to itself? No. A number is always less than or equal to itself.
Right.
Loves. Is it true that a person never loves themselves?
No.
Depends on the
No.
person.
Well, the way that we already decided this is that everyone loves themselves. We made a judgment call there, continuing with that judgment call. Is it true that a number never divides itself? No. Is it true that you never have the same last name as yourself? No. Is it true that you're never an ancestor of yourself?
Yes.
Yes. This one is irreflexive. Is it true that you're never a parent of yourself? Yes. Is it true that you are never a sibling of yourself?
Yes.
Yes. So it's quite typical that if a set is not reflexive, then it is irreflexive. Sorry. It's quite typical that for the natural relations we talk about, if it's not reflexive, then it is irreflexive. Very natural. That comes up a lot of the time, but it's not necessarily the case. But with the day-to-day relations that we talk about, it most likely is the case. So very natural that it's one or the other of these. Doesn't have to be. Okay, next, symmetric. What does it mean for a relation to be symmetric? It means for all x, y, and a, if x is related to y, then y is related to x.
Okay.
If x is related to y, then y is related to x. That's what we mean by symmetric. Is R symmetric?
Yes.
Yes.
No. Yes.
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 Anytime I have 1 related to 1, I also have 1 related to 1. If I have 2 related to 2, I have 2 related to 2. 3 related to 3, I have 3 related to 3, etc. So this one is symmetric. Is S symmetric?
No.
I have 1 related to 2. Do I have 2 related to 1? No. So it's not symmetric. W. Is W symmetric?
Yes.
Yes. Is equal to symmetric? If x equals y, is it true that y equals x?
Yes.
Yes. Is congruent symmetric?
Yes.
Yes. Is less than symmetric?
No.
If 2 is less than 3, is 3 less than 2?
No.
No. Is less than or equal to symmetric?
Yes. No. No.
Yes.
No.
If 1 is less than or equal to 2, 2 is less than or equal to 1.
But for all x.
No, it's not. What I said was nonsense.
Yeah.
If 1 is less than or equal to 2, is 2 less than or equal to 1?
No.
No. It's bigger than 1. It can't be less than or equal to 1. No, it's not symmetric. Okay. Loves. Is love symmetric? If Jack loves Jill, does Jill love Jack?
Oh
No.
no.
Divides. If A divides B, does B divide A?
No.
No.
Okay, you poor high schoolers. Love's not symmetric. Okay, divides. Divides. No, that's not symmetric. 3 divides 12. 12 does not divide 3. Okay, same last name. Is that symmetric?
Yes.
If I have the same last name as you, do you have the same last name as me?
No.
Yeah.
Yes.
Actually,
Yes,
Oh,
this one is
facts.
symmetric.
Yeah. Spaced.
What about this one? Is this symmetric? If I'm an ancestor of you, are you an ancestor of me?
No.
No. Parent of. If I'm a parent of you, are you a parent of me? No. Sibling of. If I'm a sibling of you, are you a sibling of me?
Yes.
Yes. So this one is symmetric. Alright. Next one. Anti-symmetric. Again, this is not the opposite of this. It's just names. So don't think that if you got one, you can't have the other. Well, don't think just because you have one, if you don't have one, then you have the other. That's I should have said that. Anyways, what does this one say? Anti-symmetric means that for all x, y, and a, if x is related to y and y is related to x, then x is equal to y. In other words, x is related to y and y is related to x only if they're actually the same thing.
okay.
They're only symmetric if they're the same thing. Another way to say it. So if x is related to y and y is related to x, then x is equal to y. Anti-symmetric. Starting with the first set. Is this set anti-symmetric?
Yes.
Yes?
Yes.
Yes. If you have x related to y and y related to x, you have x and y are the same thing. Okay, next one. Is this anti-symmetric?
No.
Yes, it is.
Hang on. Is it because
Every time we have 1 related to 2 and 2 related to 1, we had 1 equals 2.
Oh, yeah.
We never had 1 related to 2 and 2 related to 1.
Okay.
We can never satisfy the antecedent of this implication with that relation. So it's vacuously true. Yes, vacuously true. This is the hardest one of these relations for students to get. We never have 1 related to 2 and 2 related to 1. We never have 3 related to 2 and 2 related to 3. So the antecedent here is always false. We never have x related to y and y related to x. So this is false. False implies anything is
False.
true.
It's whatever.
True. So for all x, y, we have true. So it works. So this is anti-symmetric. And that's going to be the toughest one for you guys to get. These vacuously true statements. All right, W. Is W anti-symmetric?
Yes.
Yes. Every time I have 4 related to 4 and 4 related to 4, I have 4 equals 4. Right?
Yeah.
Next one. Equals. Is equals anti-symmetric?
Yes.
Yes.
Is it true that every time I have x equal to y and y equal to x and y are equal? Yes. Okay. What about congruent? If triangle A is congruent to triangle B, and triangle B is congruent to triangle A, are they the same triangle? No!
No.
I can draw a triangle here, and I can draw a congruent triangle here. They can be congruent.
I have one of these sides.
Whatever. There we go, 2 congruent triangles. Are those the same triangle?
No.
No! One's right here, one's right there. We have 2 triangles. They can't be the same triangle. Alright. So this one is not anti-symmetric. Next, lesson. Is lesson anti-symmetric? Is it true that every time x is less than y and y is less than x, that x and y are equal?
Yes.
Yes, it's vacuously true. We never have a number, we never have 2 numbers x and y where x is less than y and y is less than x. That can never be the case.
Right.
So the antecedent is always false. It's never the case that we have x less than y and y less than x. So this is always false, so the whole thing is true. That's why we spend so much time with implication. It can come back to bite you a lot. It's vacuously true. Okay. Less than or equals. Is this anti-symmetric?
Yes.
Can.
Yes! This one's anti-symmetric, and it's anti-symmetric in the way that makes sense. If I were to tell you that x is less than or equal to y, and y is less than or equal to x, can you conclude from that that x must be equal to y?
No.
Yeah. Oh.
Yes.
Yeah, sorry.
Right? Okay, so that one's anti-symmetric, but not in the vacuously true kind of way. It's anti-symmetric because there's tons of numbers that satisfy that, but the numbers that always satisfy that are when x and y are the same number. Okay, so this one is anti-symmetric. What about loves? If I love you and you love me, are we really the same person?
No.
No. What about divides? If A divides B and B divides A, are they the same number?
Yes.
Yes! That's why we don't think about negative 12 and 12. This was a test question, you guys. And you did your test twice. And it was a homework problem, and it's one we did in class. If A divides B and B divides A, are they the same number?
No.
No! Those are very different numbers. They both divide each other. Okay. So this is not anti-symmetric. Same last name. If I have the same last name as you and you have the same last name as me, are we the same person?
No.
No. If I'm an ancestor of you and you're an ancestor of me, are we the same person? Yes. Vacuously true. It is impossible for me to be an ancestor of you and you to be an ancestor of me. You can't be my descendant and me be your descendant.
Oh.
That's not possible.
Oh.
Okay. So yes, vacuously true. Parent of. If I'm the parent of you and you're the parent of me, are we the same person?
Yes.
Yes. Every time that happens, it's because they were the same person. Right?
Yep.
Sibling of. If I'm the sibling of you and you're the sibling of me, are we the same person?
No.
No. Okay. So we got anti-symmetric. That's the hardest one.
Yeah, I get it.
Because there's a lot of cases where it's true, but it's true vacuously. We don't like implications and definitions. Can always throw you for a loop. Let's do another one that has an implication in the definition. Transitive. And chances are you've heard of the transitive property many times before. But transitive. What does it mean for a relation to be transitive? It means for all x, y, and z in A, if x is related to y and y is related to z, then x is related to z.
Okay.
Okay?
Okay.
So let's go over an example of that. Is R transitive?
Yes.
Is it true that every time I have x related to y and y related to z, I have x related to z?
What is he?
Pick any 3 elements in A.
1, 2, 3.
1, 2, 3. Is it true that every time I have 1 relate to 2 and 2 relate to 3, I have 1 relate to 3 in this relation?
Yes.
Yes.
Yes. Pick some other 3 elements. Like 1, 1, 1. Is it true that every time I have 1 relate to 1 and 1 relate to 1, I have 1 relate to 1?
Yeah.
Yeah. So for any 3 elements I choose out of the set A, this will be satisfied.
Because it's vacuous.
Sometimes vacuously, sometimes directly. When x, y, and z are all the same number, it satisfies it directly. If I have x relate to y and y relate to z, do I have x relate to z? Yes, when all 3 are the same number. X, y, and z don't have to be different numbers, they just can be different numbers. They can also be the same numbers. Make sense? Transitive will make more sense when we get away from set examples and we get down to these ones, because that's the way you're used to seeing it. Let's continue. Is S transitive?
Why was R not transitive?
Oh, it was, sorry. Is S transitive? If x is related to y and y is related to z, do we have x related to z?
No.
Well, if 1's related to 2 and 2's related to, well, we don't have 2 related to anything, so we can't really continue that chain. So it's going to end up vacuously true, because we can't get this string of chains. If 3's related to 2 and 2's related to, we don't have 2 related to anything. So it's going to be vacuously true no matter how we think about it. So this one is transitive. You cannot come up with an example where we have x related to y and y related to z, but we do not have x related to z. You cannot find an example that works here. You can't find an example that makes it false.
Yeah.
That's probably the best way to think about these relation properties. Can you find an example that makes it false? If not, then it's true. Alright, let's try W. Is W transitive?
Yes.
Is it?
Yeah. 4 related 4 related 4.
What do you think, Debbie?
Yeah.
Yeah? Is that the answer everyone's saying? Alright. Next, equals. Is equals transitive? If x is equal to y and y is equal to z, is x equal to z?
Yes.
You sure?
Yes. Positive.
You're positive. If I know that x is equal to y and y is equal to z, do I know that x is equal to z?
Yes.
Yes. So equals is transitive. Okay. What about congruent? Is congruent transitive? If triangle A is congruent to triangle B, and triangle B is congruent to triangle C, is triangle A congruent to triangle C?
Yes.
Unequivocally.
Yes. So this is transitive. Is less than transitive. If A is less than B and B is less than C, is A less than C?
Say that again.
Yes.
If A is less than B and B is less than C, is A less than C?
Yes.
All right. So this is transitive. What about less than or equal to? Yeah. What about loves? If Jack loves Jill and Jill loves Frank, does Jack love Frank? No. So it's not transitive.
Definitely does not like
Divides. If A divides B and B divides C, does A divide C?
Yes.
Yes, we proved that one.
Yes.
I'm glad you all said yes on one we proved. Okay. Same last name. If I have the same last name as...
Right. Just
Oh, thank you. Transitive. Okay. If I have the same last name as Jack and Jack has the same last name as Jill, do I have the same last name as Jill?
Yes.
Yes. Ancestor of. If I'm an ancestor of Bob and Bob's an ancestor of Frank, am I an ancestor of Frank?
Yes.
Yes.
If you're Bob's parent and Bob's
If I'm an ancestor of
Bob's parent.
Bob and Bob's an ancestor of
Oh.
Frank, am I an ancestor of Frank? Yes. Shoot, we probably went off the screen with that illustration. That was my big one. Maybe not. Okay, anyways. Parent of. If I'm a parent of Jack and Jack's a parent of Jill, am I a parent of Jill?
yeah.
No.
No.
A grandparent.
I'm a grandparent, not a parent. Alright. Sibling.
Yes.
Yes.
Sibling's transitive?
Mm-hmm.
Yes.
It's not.
What? Why?
Yes, it is.
Can anyone explain to me why it's not transitive?
Because you can have like stepmom, like.
No, overthinking it. We'll assume that sibling means two common parents.
It is transitive.
It
You're
is,
adopted.
if I'm siblings with Jeremy and Jeremy's siblings with Chandler, then I'm siblings with Chandler.
True. Now, if you're siblings with Jeremy and Jeremy's siblings with you, are you siblings with you?
Got him. That's hex.
Oh.
So you got to be able to come up with these corner cases,
Okay.
I see.
right? So
Yep.
this one is not transitive.
Okay.
Good?
Good.
Sure.
Wonderful. So there's an example of a bunch of relations trying to get you familiar with these 5 properties. You need to get familiar with these 5 properties. The 3 key ones are these ones. These ones never go away. And we have a special name for relations that have all those 3. We call them equivalence relations. So anyone that has R, S, and T is an equivalence relation. So one's like that. That one, that one. Same last name, and what's going to be one? Anyways, doesn't go away. So get familiar with these things, but yeah, that's all we have for today with relations. Any questions you want answered on lecture before we move to homework?
No. Do you have the same